Welcome to Lecture 4 of Geometric Physics 1. Today is called Integration, Stokes and Maxwell. The reading is Frankel, sections 2.8 through 2.10, and all of Chapter 3. For next time, read Frankel sections 4.1 through 4.3. Problem set 1 is due at the start of this class. Today we take the machinery we spent 3 lectures building, and we finally spend it. We now have K-forms, the wedge product, the exterior derivative d, and the pullback f star. Today we cache all 4 of them in. There are 5 stops. First, orientation, and the pseudoforms that physics uses everywhere without ever naming them. Second, the interior product with a vector field x, which completes the R3 dictionary we started last time. Third, integration of forms, and the reason integration is automatically independent of how you parametrize. Fourth, Stokes' theorem, which contains all of vector calculus at once. Fifth, Maxwell's equations, written in 2 lines. Here is the promise for the hour. 2 of Maxwell's equations are usually stated separately. One says the divergence of B is 0. The other is Faraday's law. By the end of today, both will have collapsed into the single equation dF equals 0. And charge conservation will turn out to be a corollary of D is 0. We start with orientation, and with a class of objects that physics uses constantly and almost never names out loud, the pseudoforms. An orientation of an n-dimensional vector space is a choice between the 2 equivalence classes of ordered bases. 2 bases are equivalent when the change of basis matrix has positive determinant. Equivalently, an orientation is a choice of a non-zero top degree form up to positive scale. That version lifts straight to manifolds. A manifold M is orientable if it has an atlas whose transition maps all have positive Jacobian determinant. Equivalently, M carries a nowhere vanishing n form, called a volume form. Spheres are orientable, so are tori, and so is every Lie group. Real projective 2 space is not, and neither is the Möbius band, which admits no consistent normal. Now the case we care about. Every cotangent bundle T star Q is orientable, whether or not Q itself is. The reason is that omega wedged with itself n times never vanishes. Phase space always has a volume, and its conservation is Liouville's theorem. An ordinary K-form changes sign under a change of chart in the usual tensorial way. A pseudo K-form picks up 1 extra factor, the sign of the determinant of that change of chart. Pseudoforms are also called twisted forms, or odd forms. The examples are familiar. Mass density is a pseudo-n form because the total mass of a body cannot depend on which orientation you picked. The magnetic field B is a pseudo-2 form. Angular velocity, torque, and any cross product of 2 vectors are pseudo-objects. So are charge density and current density. So here's the point. The word pseudovector in a physics course is not a warning about reflections bolted on after the fact. That word is the statement that the object is a pseudoform, and the sign rule is forced by what the object is for. Pseudoforms integrate over unoriented submanifolds carrying a transverse orientation. That is exactly flux through a surface with a chosen side. One operation is still missing. Take a vector field x and a K-form alpha. The interior product of x with alpha is a K-1 form. You build that form by feeding x into the first slot of alpha. The interior product is an antiderivation of degree -1, and doing it twice with the same x gives 0. Now the R3 dictionary closes. Curl is the statement that D of a flat equals the interior product of curl A with the volume form. Divergence is the statement that D of the interior product of A with the volume form equals the divergence of A times the volume form. And the cross product of U and V is the interior product of V with the interior product of U with the volume form. That last line tells us why the cross product exists only in 3 dimensions. Only there do 2 forms and 1 forms have the same dimension. The correct general object is the double interior product with the volume form, and that object exists in every dimension. With orientation in hand, we can finally integrate. This is where the whole apparatus of the last 3 lectures starts paying for itself. Let phi parametrite a k-dimensional piece of M, mapping an open set U in Rk into M, and let alpha be a K-form. Pull alpha back along phi. Because U is k-dimensional, the pullback has to be a single function A of U, times du1 wedge through duk. There is only one top degree form on u up to scale. So we define the integral of alpha over phi to be the ordinary multiple integral of a. Now the payoff reparametrat, replacing phi by phi composed with an orientation preserving diffeomorphism h. Then psi star alpha equals h star of phi star alpha, which is composed with h times the determinant of the derivative of h. Change of variables asks for exactly the absolute value of that determinant, and h preserves orientation, so the absolute value is the determinant itself. The two integrals agree. Sit with what just happened. The Jacobian was not inserted by hand to make the answer come out right. The Jacobian is the pullback. That is, the entire reason forms are the correct integrands, and no metric appeared anywhere. Integration is defined before any notion of length exists. Two pieces of bookkeeping before Stokes. First, manifolds with boundary. M is a manifold with boundary if its charts take values in the closed half space in Rn, where the last coordinate is greater than or equal to 0. The boundary of M is the set of points mapping to last coordinate 0. That boundary is an n-1 dimensional manifold, and it has no boundary of its own. Second, partitions of unity. Given any open cover of a second countable manifold, there are smooth functions chi sub a. Each key lies between 0 and 1 and is supported inside its own patch. The family is locally finite, and the whole family sums to 1. Partitions of unity let us chop a form into pieces, integrate each piece in one chart, and add up. So for compact-oriented M and a top degree form alpha, the integral over M is the sum of those chart-by-chart integrals. The proposition we just proved says the answer depends on no choice we made. This is where second countability earns its place in the definition of a manifold. No partitions of unity, no integration, no Stokes, no Hodge theory, and therefore no quarter 2. Here it is. Let M be a compact-oriented n-manifold with boundary. Let the boundary carry the induced orientation, and let alpha be an n-1 form on M. Then the integral over M of d alpha equals the integral over the boundary of M of alpha. That is the whole theorem, and the proof is almost anticlimactic. Use a partition of unity to reduce to a single chart. In the half space, the statement becomes the fundamental theorem of calculus in the last coordinate direction. Every other term integrates to 0 because the forms have compact support. So why does something this short carry so much? Look at the shape of the statement. One side applies d to alpha and integrates over M. The other side integrates alpha itself over the boundary of M. The exterior derivative is traded for the boundary operator. In other words, d is the adjoint of taking boundaries. Read Stokes that way and the whole subject reorganizes. The exterior derivative is defined so that this holds. Every property of d is the shadow of a property of taking boundaries. And d of d is 0 is the dual of the statement that a boundary has no boundary. One theorem, 4 classical names. Take n equal to 1 and m an interval. Then Stokes says the integral of f prime from a to b equals f of b minus f of a. That is the fundamental theorem of calculus. Take n equal to 3 and m a solid region. Then Stokes says the integral of the divergence of A over the region equals the flux of A through the boundary surface. That is the divergence theorem. In between Sitt-Green's theorem in the plane and the Kelvin-Stokes theorem for a surface in R3. Same theorem 4 times. There is a corollary worth stating on its own. If M has empty boundary, then the integral over M of d alpha is 0. On a closed manifold, an exact top form integrates to 0. Now turn that around. A closed form with a non-zero integral over some cycle cannot possibly be exact. Made systematic, that single observation is de Rham cohomology, and it is what detects monopoles and instantons. On an oriented Riemannian manifold, there is exactly one n form taking the value 1 on every positively oriented orthonormal frame. In coordinates, that form is the square root of the determinant of g times dx1 wedge through dxn. In polar coordinates in the plane, the determinant of g is r squared, so the volume form is r dr wedge d theta. In spherical coordinates, the coefficient is r squared sine theta. One contrast before the punchline. On t star q, the form capital lambda, 1 over n factorial times omega wedged with itself n times is a volume form built from omega alone, with no metric anywhere. Hamiltonian flows preserve omega, so they preserve capital lambda. That is Liouville's theorem, a one-line corollary rather than a computation, and Lecture 7 does it properly. So here's the idea to keep. Every square root of g in a physics calculation is the coefficient of a volume form. The square root of g appears because a function is not something you can integrate on a manifold. Only an n form is multiplying by the square root of g converts one into the other. Back to pseudoforms, now that we can integrate. To integrate a pseudo K form over a K-dimensional submanifold S, you do not orient S at all. You orient the complement. You choose a side. That is precisely how flux gets measured in a laboratory. You decide which way is out. You do not decide which way is counterclockwise. And that is why the flux of B through a surface makes sense even across a non-orientable surface, as long as a normal side has been chosen. The corresponding integral of an ordinary two-form would not make sense there. One consequence worth naming. Gauss's law, the statement that the integral of E over the boundary of a volume equals the enclosed charge, is a statement about pseudoforms. The enclosed charge is a pseudo-3 form. The traditional business about which vectors flip under a mirror is this same distinction, seen from the wrong side. An example that matters later. On R3 with the origin removed, define a two-form sigma. The numerator is x dy wedge dz plus y dz wedge dx plus z dx wedge dx plus z dx wedge dy. The denominator is the distance from the origin cubed. 3 facts. A direct computation gives d sigma equals 0 away from the origin. On the unit 2 sphere, sigma is the standard area form with integral 4 pi. And by the corollary just proved, a closed form with a non-zero integral cannot be exact. So no global one-form beta has d beta equal to sigma. Dirac's argument runs on exactly this. If a monopole existed, there would be no global vector potential, only potentials on patches, requiring the wave functions to agree on the overlap forces 2Eg over h bar c to be an integer. Here g is the monopole strength, so the flux is 4 pi g. Charge quantization out of a cohomology class. Lecture 30 does this properly. What sigma really is. It is the field of a unit point charge and also of a magnetic monopole. The obstruction is topological. The second cohomology of the punctured R3 is one-dimensional, generated by sigma. Everything we have built now gets spent at once. Maxwell's equations in 2 lines with charge conservation thrown in for free. Work on Minkowski spacetime with coordinates t, x, y, and z. Before writing any equation, ask the question that organizes everything. What kind of object is each field? The answer comes from how each field is measured. You integrate the electric field along a wire, so the electric field is a one-form on space. You integrate the magnetic field over a surface to get flux, so the magnetic field is a pseudo-2 form on space. Charge density is integrated over a volume, and current across a cross-section, so both are pseudoforms of degree 3 and degree 2. And you integrate the potential A along a world line to get an action, so A is a one-form on spacetime. Notice that no convention entered anywhere. The degree of each field is dictated by what you integrated over, which is dictated by how it is measured. The traditional confusion about which fields are really vectors evaporates once you ask in that order. Now assemble the electric and magnetic fields into a single object on spacetime. Define F in 2 pieces. The first piece is E sub I dxi wedge dt. The second is the 2-form built from B, namely 1/2 epsilon ijk bi dxj wedge dxk. So F is a 2-form on 4-dimensional spacetime, and F is called the Faraday 2-form. Now compute df and sort the result by type. The purely spatial part comes out proportional to the divergence of B times dx1 wedge dx2 wedge dx3. The mixed part, the part carrying a dt, comes out proportional to the time derivative of B plus the curl of E. So setting df equal to 0 gives us in one stroke 2 of Maxwell's 4 equations. The divergence of B is 0, and the time derivative of B plus the curl of E is 0. Sit with that, two of Maxwell's four equations say nothing physical about matter at all. Those two equations say only that F is a closed two-form. They hold in any space-time, with or without a metric. They are geometry, not dynamics. The other two equations are different in kind. They need the metric. The metric enters through the Hodge star, which turns a K-form into an n minus K form. Lecture 26 does the Hodge star properly. Package charge density and current into 1,3 form J. Then the second pair is the single line D of the Hodge star of F equals J. Unpacked, that says the divergence of E is rho, and the curl of B minus the time derivative of E is J. Now apply D to that equation. One side gives dJ, the other gives d of the Hodge star of F, and d of D is 0. So dJ equals 0, with nothing assumed and nothing added. Unwind dJ equals 0 in components, and it reads that the time derivative of rho plus the divergence of J equals 0. That is the continuity equation, and that is charge conservation. So charge conservation is not an extra law. Charge conservation is forced by d of D is 0, which is to say by the equality of mixed partial derivatives. A theory whose field equation is d of the Hodge star of F equals J cannot violate charge conservation. One more consequence. dF is 0, so F is closed. On a contractible region, the Poincaré lemma says a closed form is exact. That is Lecture 9. So F equals dA for one form A on spacetime. In components, A is minus phi dt plus a sub I dxi, but A is not unique. Take any function chi and replace A by A plus d chi. Then d of A plus d chi equals dA plus d of d chi, and d of d chi is 0. So we get F back unchanged, and every physical prediction is left alone. That is gauge freedom, and in components it is familiar. Phi goes to phi minus the time derivative of chi, and the vector potential A goes to A plus the gradient of chi. Lectures 28 through 30 pick this up, and Yang-Mills arrives in lecture 36. Two things to carry forward. First, the phrase on a contractible region is a real hypothesis. Where that hypothesis fails is exactly where the Dirac monopole lives. Second, and this is quarter 2 in one sentence, A is a connection, F is its curvature, and d chi is an infinitesimal change of trivialization. 6 things from today. 1. Orientation is a choice of a class of ordered basis, equivalently a nowhere vanishing top form. Every cotangent bundle T star Q is orientable, so phase space always has a canonical volume. 2. Physics is full of pseudoforms. The magnetic field, charge density, current, torque. Pseudovector is a statement about a twisted form, not a footnote about mirrors. 3. The interior product completes the R3 dictionary, and the cross product is a double interior product with the volume form. 4. The integral of alpha over phi is the integral of the pullback of alpha, and that is parametrization independent because the pullback is the Jacobian. 5. The integral over m of d alpha equals the integral over the boundary of m of alpha. That one line contains the fundamental theorem, Green's theorem, Kelvin-Stokes, and the divergence theorem. 6. dF equals 0 and d of the Hodge star of F equals J are Maxwell's equations. J equals 0 is a corollary of d of D is 0, and F equals dA is gauge freedom. With that, the geometry review is over. Lecture 5 does the Lie derivative. Lecture 6 opens Marsden and Ratiu, and the symplectic structure appears for real. From here on, this course is mechanics, and from week 4 the two texts run in parallel.